So this is a video of a linear programming question. And luckily this will not be on the review for the final exam, because I'm pretty sure it's not, which is why there's not a video of it. So I'm going to try to go through this with you and kind of pick out some key components of the question so that you can see how to set it up. So this question says, a mining company owns 2 mines. These mines produce an ore that can be graded into 2 classes, regular grade and low grade. The company must produce at least 350 tons of the regular grade. So I'm going to circle this at least, because as soon as you see an at least or at most, then that tells you what your inequalities are going to be. So if it's at least 350 tons, that means it has to be greater than or equal to 350 tons of what? Of the regular grade. So this is my regular grade. So the other part, 610 tons of the low grade, we're still talking about at least 610 tons of the low grade. So at least 610 tons of the low grade. And the reason I do this is because then this tells me that everything in this inequality must be in reference to regular grade, and everything in this inequality must be in reference to the low grade. So that's helpful for me because I know that I have 2 mines. And I may have thought, well, maybe this whole inequality is mine 1 and this is mine 2, but it can't be, because the at least referenced this 350 of all regular grade. So this kind of gives me the definition of what that sentence will be. So the only other place to put the mines then would be here and here. So I'm going to call mine 1 X and mine 2 Y. So I'm going to have an X and a Y for this inequality and an X and a Y for this inequality. So as I continue to read, it says the first mine produces 5 tons of regular grade. So this is the first mine, it's 5 tons of regular grade. So it has to go in the regular inequality. And it gets an X because I decided that mine 1 was X. Okay, and 17 tons of low grade. So we're still mine 1, low grade has to go in this inequality, so I'm going to go 17X there. All right, the second mine produces 20 tons of regular grade. So 20 of the second mine, regular grade, that gets a Y, and I'm going to add those 2. And then 10 tons of low grade. So low grade, this would be 10. All right, so now this is great because I have my 2 most difficult inequalities of the question. So what else do I know about these? All right, so if I keep reading, I'm right here, right? So the operating cost, well, as soon as it goes into a cost, then that's going to be your profit or your cost function. So everything from here down to here is its own equation, and that's the equation that we're going to use in the end to test to see where I get my minimum point. So what would that equation look like? The operating cost of the first mine is 18,000, so that's going to be 18,000 X, because that's the first mine, right? And then the second mine is 10,000, so plus 10,000 Y, and that's my cost function. I'll slide this over. So that's my cost function, because they said that that is the operating cost. All right, so I've dealt with everything down to here. And then it says the first mine can be operated no more than 54 hours a week. So this is a constraint. We're talking about mine 1. So mine 1 can't be more than 54 hours, so it has to be less than or equal to 54. But we also know that it has to be greater than or equal to 0, because you can't have a negative there. You can't mine for a negative number of hours. All right, and then it says, and the second mine can be operated no more than 27, so Y has to be less than or equal to 27, and of course, it's also going to be greater than or equal to 0. And then they finally get to the actual question. So here's the question. How many hours per week should each mine be operated to minimize the cost? So this is what we're going to finally answer. and we're talking about minimizing the cost, which is why we need the cost function. And so what I'm going to do is I'm going to graph these four inequalities basically, and then I'll find my solution region, which is where all of these intersect. And once I find the solution region, then I'm going to find the values of all the intersecting points, all the corners of that region. And once I get all those corners, I'm going to plug each point into this cost function to see which one is the minimum, and then that will be my answer. All right, so let me first graph this line, 5x plus 20y. It's an inequality, so the first thing I do is I graph it as an equation. So 5x plus 20y equals 350. So this will give me the line itself. You can like reduce this if you want, divide everything by 5. It's the same thing to get x plus 4y equals 70. So if you'd rather graph that, that might be easier. If you want to choose to make this y equals mx plus b by solving for y, if you prefer to graph that way, you can. You could also do the zeros method. So if x is 0, then y would be 70 divided by 4, which is whatever that is, which is 35 over 2, which is 17.5. So when x is 0, then I make that 0, then y would be 17.5. So 0, and then let's do these by 5s. 5, 10, 15, 17.5. So I'm right there, okay? If y is 0, so if I make y 0, I shouldn't have erased that one, then this becomes 0. Then I get 5x equals 350. So x is going to be 70. So when y is 0, I get 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70. So I'm all the way out here, okay? So this is the first line right there. I'm going to label that line 1 so that later I know where it came from. So this is line 1. And let's see. It's helpful to go ahead and put these points in. So this was when x was 0, y was 17.5. And then this was when y was 0, x was 70. And I may not need those points later, but it's helpful to put them in now so I don't have to go back and kind of get my head back into this particular equation. Now, it's actually an inequality, right? So what side would be shaded? So greater than or equal to. We could do a test point, and let's test the point 0, 0. If I put 0, 0 in for x and y, I would get 0 plus 0, which is 0, is greater than or equal to 350. Well, that's not true. So therefore 0, 0 is not in my solution space. So it must be the other side of the line that is my solution space. So I've graphed that line. Notice I cut it off here, and that's because I knew that x was greater than or equal to 0. So we're already constrained by being in the first quadrant because x is positive and y is positive. We already know that. We could get these out of the way. So x is less than or equal to 54, which means I would have 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 4. So I'm going to have a line right there. I'll put that in red. So that's going to be going this way. Okay. Oops. And x is less than or equal to 54. So that's going to be coming. So we're shading this side. So I'm trying to find where these intersect, right? All these different colors. We could go ahead and get the y out of the way as well. So I have, obviously y is greater than or equal to 0, so I'm up here. And then y is less than or equal to 27. So that would be 5, 10, 15, 20, 25, 27 is right about there. So we're starting to see our region become a closed space, but I still have one more inequality to graph, right? And less than or equal to 27, so the green would be down this way. Okay, again, it's helpful to go ahead and label the points. So this point is x was 54, y was 27, 54, 27. And I may end up needing this point, I'm not sure yet, and that one I'm not sure yet, so I'll just wait a minute for those. All right, let's do the other line, this one right here. So I have 17x plus 10y is greater than or equal to 610. So if I use my zeros method, if I make x 0, then I get y equals 610 divided by 10 is 61. If I wrote that right. Yeah. So that's the point when x is 0, y is 61, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 61 is probably somewhere up there, right? And then if y is 0, I get x equal to 610 divided by 17. So when y is 0, 610 over 17, we'll need a calculator for that. Give me 1 second. Sorry, I don't actually have a calculator, so I have to do it by hand. So 10, 100. So it's about 35. It's 35 and some change. So it's 35 point something. So that was when y was 0. X was 35 point something. So I'm gonna go 5, 10, 15, 20, 25, 30, 35. So I'm right about there. So that makes this line come like this, okay? And then what side would be shaded? Well, if I try my test point of 0, 0, I put 0 in and 0 in, I get 0 is greater than or equal to 610, which is not true. So it's not gonna be the side of the line that has the 0, 0, it'll be this side of the line. So that's my solution region, is right there. And so I can erase all this, I don't really need it anymore, right? And erase all that, erase all this and all that, okay? Because this is the region that I care about. And I've got 4 corners. 1, 2, 3, 4. 2 of them I've already got my coordinates for. So if this came from the first line, this was my second line, so I'm going to label that 2 right there. So I need to know the coordinates of this corner and then that corner. So this corner would be the intersection of line 2 and the constraint y is less than or equal to 27. So in other words, I'm gonna see what happens when y is 27. That's the line y is 27. What do I get in this equation? So I have 17x plus 10 times 27 equals 610. So 17x plus 270 equals 610. Subtract 270. I get, I'm going to write it over here, 17x equals 340, which is nice because when I divide by 17, I get x equals 20. So what happened was when y was 27, x was 20, that's this point. So this point is the point 20, 27. And now I need to find this corner. Well, this corner is the intersection of lines 1 and 2. So now I've got to find what happens when I combine lines 1 and 2. So line 1 is 5x plus 20y. We'll use equals because I care about the line itself and not the shading on the left and right in this particular part of the question. And then I've got 17x plus 10y equals 610. So how would I find where those intersect? Well, one way you can find it out is using the addition method. So let's say if I made this a negative 20 here by timesing by negative 2, my new line would be negative 34x minus 20y equals negative 1220. I'm going to put a little line through that one so I don't look at that when I'm doing my adding. So 5x minus 34x is negative 29x. Then the 20s go away, equals 1220 minus 350 would be 870, I believe. And then I would divide that, I'm sorry, it'd be negative 870 divided by negative 29. So, let's see, I think that's exactly 30. Because 3 29s, and again, if you had a calculator, I don't have my calculator on me, and I usually use my phone, but I'm using that to record right now, so I apologize for the extra time it's taking. But this becomes a 30, okay? So they intersect when x is 30. Well, if x is 30, then what is y? So what I could do is then put the 30 back in for either of these x's and then solve the equation. This one looks easier to me. 30 times 5 is 150 plus 20y equals 350 minus 150, I get 20y equals 200, divide by 20, then y is 10. So this intersecting point is 30 comma 10 right here. So I now have my 4 corners, and what I need to do is test each of those corners into this cost equation. So let me erase all this and let me list them out. So I've got 20, 27, that's one of them. I've got 54, 27. I've got 30, 10. And I've got 70 and 0. No, I'm sorry. Oh, you know what? I didn't find this corner, did I? This 70, 0 is all the way out there. So this corner would be the intersection of line 1 and x is 54. So line 1 and x is 54. I'd put a 54 in to line 1. So x is 54 plus 20y equals 350. 5 times 54 is 270. Minus 270, I get 20y equals 80. So y equals 4. So that's the point 4 comma 54 right here. I'm sorry, 54 comma 4. So x was 54, y is 4. So those should be my 4 corners. And what I'm going to do then is I'm going to list those 4 corners. So I have 54 comma 4 as my last one. And now I'm going to test all of those in my cost function. So is this a lengthy problem? Absolutely. A lot of room for error, unfortunately. So this would be 18,000 times 20 plus 10,000 times 27. And I did this part ahead of time, so it'd be quicker not to use my calculator since I don't have one. So I get 630,000 for that one. So this one would be 18,000 times 54 plus 10,000 times 27. And for that one, I got 1,242,000. Here I get 18,000 times 30 plus 10,000 times 10. And that is 640,000. And then finally I get 18,000 times 54 plus 10,000 times 4. And that ended up being 1,012,000. Okay, so those are all my test points. So I tested each of these 4 corners of my solution region. And I'm looking for how many hours per week should each mine be operated to minimize the cost? Well, this is the smallest. This is the minimal cost. So therefore, it would be 20 went in for X. So that would be mine 1 is 20 hours, and then mine 2 was 27 hours. So that would be the answer to that big question. All right, I hope this was helpful. Feel free to contact me if you want any more detailed explanations.